In this section, we'll review set properties and axioms, and most of these should be pretty familiar to you based on basic mathematics. A lot of these rules will look very similar to those that you've already seen, but it's important to recognize that these still apply to probabilistic systems. And so we'll do a quick review of several of those rules and laws within this section. So the first thing that we'll look at is some of the laws of sets. And you'll notice I have two categories here, the associative laws and commutative laws. And if you remember from basic math, these are pretty much the same thing. So the first one we'll look at is that A unioned with B, that quantity then unioned with C is equal to B unioned with C, that quantity then unioned with A. Now, this looks pretty familiar from our basic days of algebra when we said that an A plus B then added to C is equal to an A plus B plus C. This is basically the same rule. We're saying that we can move parentheses around within unions and order really doesn't matter. They're the same thing. The other associative law is for intersections. And again, saying basically the same thing, that parentheses don't matter. An A intersected with B, that quantity then intersected with C, is equal to an A intersected with the quantity B intersect C. Again, should look very familiar to what you remember from basic mathematics, just knowing that parentheses don't matter when it comes to unions or intersects. You can move those around and they will operate the same. Now I say that applies when it is a like operation. We will look at dislike or different operations here in a little bit. The next thing we'll look at is the commutative laws, and the first one is that A union B is equal to B union A. So saying that when it comes to a union, the order of the operands, which one comes first, does not matter. Same thing applies for intersects. When it comes to the intersects, the order of the operands does not matter, saying that A intersect B is just equal to B intersect A. Now looking at some of the additional laws of sets, we can look at the distributive laws. And this is saying that when I have an intersect multiplied by a union, so we're saying that A intersected with the union of B and C, that we can distribute that A intersected into two different quantities. And so that becomes A intersected with B, then unioned with A intersect C. And this should make fairly good sense based on some of the things that we've looked at already from basic mathematics, but we'll do a quick graphical example here. If we first look at B union C, we're looking at all of this area plus all of this area, and that is B union C. Now, when we intersect that with A, all that we're going to be left with is the area where A is intersected or is combined, is also there with this red shaded area. And so that is going to be this area here shaded in black. Now, looking at that from a slightly different perspective, we look at the other side of that argument. We can first do A intersected with B, which is all of this area here. And then we can union that or add it to A intersected with C, which is all of this area here. And you'll notice that the area that we're left with is still all of this area in the middle, which is the same as what we had before. Now, the other distributive law is basically flipping the operators. So instead of having an intersection of a union, we now have a union of an intersection. And again, the same distribution follows, that we can take the A unioned with an intersection and move that to be independent for both arguments. So we can say that A unioned with the intersection of B and C is equal to A unioned with B intersected with A unioned with C. And again, just to prove this, we'll look at it graphically. If we first look at B intersected with C, we're going to find that that is this area here. And when we union that with A, we're basically just adding all of the rest of A. So we end up with the entirety of A plus this little area here down from B and C. Now, if we look at this the other way and look at the right-hand side of this operator, we're saying that that is theoretically equal to A unioned with B intersected with A unioned with C. So if we look at A union B, that is all of this area here. If we look at A unioned with C, that is all of this area here. Now, if we look at the intersection of those, we're looking for basically anywhere that we have both red and blue. And so if we come back and put that in black, what you'll find is that we have both red and blue for the entirety of A, as well as this little bit here of B and C. So again, we end up with the entirety of A and this little intersection of B and C down here in the corner that is, again, the same as what we had with the left-hand side of this argument where we said that A unioned with the intersection of B and C is now equal to, at least graphically and mathematically, the intersection of the union of A and B and the union of A and C. Again, basically just showing that these laws hold up. Now, there's a couple laws that we'll go through pretty quickly, and we won't spend a ton of time here, but they are important for you to recognize. Again, they follow pretty much from basic mathematics, and they're pretty intuitive. So we'll go through them fairly quickly, but the first one we'll look at is the identity law that A unioned with the empty set is just equal to A. This is effectively saying the same thing as A plus 0 is equal to A. The other identity law is that A intersected with omega is still just equal to A. Again, omega, based on some of our axioms of probability, we know that omega is everything. It is equal to 1. And so when we say, give me the combination where I have both what's in A and it also has to be in everything, well, saying that it's also in everything is pretty much irrelevant. You're already limited to just that which is A. The other laws that we'll look at are the bound laws, and that basically says that if I union A with everything, with omega, with the world, if I say it has to be part of A or part of everything, well, everything is everything including A. And so in this case, we say that that's just equal to omega. It's equal to everything. The other bound law is the opposite side, saying that if I take A intersected with the empty set, I'm just left with the empty set. If I say, give me everything that is in both A and nothing, well, since nothing has nothing, then it doesn't matter what's in A, it can't be in both of them because the empty set is nothing. So again, just saying that that is the empty set. There's also these things called the idempotent laws, and they basically say that if I union A with A, I get A, and that if I intersect A with A, I get A. There's also the complement laws that say that A unioned with A complement is equal to omega. So again, we've said that based on the definition really of A complement, that is, give me everything in omega, everything in the world that is not A. If I union that with A, then I'm left with everything. And the opposite is also true. If I say give me the intersection of A with its complement, that's equal to the empty set. Again, basically just saying the complement is everything that is not A. And so if it's everything that is not A, then there's nothing in common between A and A complement. The next law we'll look at is what's called the absorption law. And ultimately what we'll see here is some simple equations that ultimately simplify pretty quickly. And so the first one we'll look at is that A unioned with the intersection of A and B is just equal to A. So if I look at this graphically, then I can say that if I look at the intersection of A and B, that's this middle area here, and that if I then union A with that, I'm left with what looks like A. And the second absorption law is that A intersected with the union of A and B is also equal to A. And so if I look at the union of A and B, that's going to be all of this area here. And if I intersect that back with A, then I'm only looking at the area where I have both blue and red, and what we'll find is that that is just A again. So the absorption laws are pretty straightforward, but sometimes you'll get in a situation where you can apply these very quickly to say that in this case, it doesn't really matter what B is. It's irrelevant. I'm just going to be left with A. So these are some of those laws that are useful to keep around in your bag of tricks as you're trying to solve probability to eliminate some potentially irrelevant events. In this case, B. Now, there's also the involution law, which basically says that if I take the complement of a complement, I'm left with just the original argument. So in this case, A double prime, or the complement of A's complement, is just equal to A again. So we're saying that it is a complement of a complement, a double complement, and that just returns us to the original element. Now, the 0-1 laws are another set of laws that basically state that the empty set's complement, or the complement of nothing, is everything. It's omega. And that the complement of everything, everything that is not everything, well, there's nothing left. So you're left with the empty set. And while these may seem trivial, they are kind of important when it comes to proving a lot of these things mathematically.